Welcome to video number 13 in the Fortitudo.tech Python package walkthrough. In this video we'll be going through the high-dimensional CVaR portfolio optimization example. So as always we start at the front page of the repository and then navigate to the examples. So here you can see that example number 13, it's called high-dimensional CVaR, and this is specifically for portfolio optimization. So basically the idea for creating this example came from comments from people who usually come up with excuses for not using CVaR and continue to use variants. So one of the excuses that they make is that we do not have enough data for CVaR optimization. However, if you look at this Substack article called Better Backtesting, so I encourage you to go in and look there, where you compare CVaR to variance optimization, you see that actually something like 10 observations for the tail can be sufficient when you perform CVaR optimization. But it's also based on how different your assets are. If they are quite similar and you have a market of 10 investable instruments, as in this case, well, then it's not required for us to have a lot of observations in the tail before we can build portfolios in a smart way. So this is an interesting side effect from this Better Backtesting article. So make sure to check it out because it's also an interesting case study related to the portfolio construction and risk management book. So the other example is that some people they say, oh, but does CVaR work in high dimension? Let's say if I have a equity portfolio of 2,000 different stocks and I want to optimize that. Is that possible to do with CVaR? And the thing is that this example, it shows that it's definitely possible to do it, even with this simple open source implementation that we have. And actually it runs in a faster way than variance optimization. So the point is that it seems that mean CVaR optimization becomes even more natural in higher dimensions, and it avoids all the issues with estimating covariance matrices and all these things that people they talk about when they do mean variance. So yeah, this is what we'll be going through today, and just to show you how we generated this example. And if you want to read more about CVaR optimization and entropy pooling and the resampling method that we use for market simulation here, then make sure to check out the portfolio construction and risk management book on this link. All right, there's also a high-level description of this case study in this on Substack, called high-dimensional CVaR optimization. So you can also look into that as supporting material. All right. So the first step is just to import the package that we need, and here we use this open source Fortitudo.tech Python package, and then Y-Finance to get the data, and then otherwise standard packages for data analysis and timing of this optimization. So first we get some index data, and this is the same equity data that we use in chapter 2 of the portfolio construction risk management book to analyze equity stylized markets facts, and it's also the same data that we use in the normal distribution myth article, where we perform some formal tests for normality of returns on different horizons that we can very clearly reject. All right. So here we download all these US equity indices, and we also get the VIX index so that we can use it for simulation in our time and state dependent resampling method. Okay, so here we just show you some statistics of how much data we have, and then we proceed to the simulation. So here we use the fully flexible resampling method, which was first introduced in chapter 3 of the portfolio construction risk management book, to simulate 21 trading days ahead. So here in this explanation you have many references, so for you to understand how this method works and go into the details, here we will just apply it, and actually most of the code that we use here, it's from example 11, so that you can also find a video walkthrough of that one. All right, So the idea is that we use these 10 equity indices and then we use VIX as the state variable to simulate 10,000 new scenarios for the future. And then after that, we compute some random factor loadings, 2,000 different to these factors, to try to simulate some fictitious stock returns. The point is that it's not so essential whether these are actual stocks. It's more essential that we get some simulations that are high dimensional, so 2,000 instruments, and that has something which is non-normal, just to show you that CVaR optimization will work for fully general distributions. And then we also perform some stress testing there, and then finally we compare to variance optimization. So first we compute the log returns, and we just illustrate some statistics for the daily ones, how they are. So you can see, as we already know, a lot of skewness, a lot of fat tails in this. And then we extract this VIX index and compute some conditioning values. So basically what we call high, medium, and low VIX. So yeah, this is also from previous examples, and here we just illustrate like how we have categorized the historical VIX states. In this case, what we mean by low and mid and high. All right. So after that, we use this fully flexible resampling method, and in this case, we create this exponential half-life. So basically we just say that a half-life parameter that we set to half of the observations. So basically what that means is that if we go back half of the observations from the latest observation, well, then the probability of that observation in the prior will be half of the latest observation. It's something that you can look into also with the other examples where we go into more details. But this is the time conditioning in this fully flexible resampling method, and then we use the VIX index and the values of that for the state conditioning. So this we perform with entropy pooling, and here you can see how it's done in a low-level way. As long as it's for just one state variable, it's maybe okay to do it like this. But when it becomes multiple state variables, of course, you need some nicer code to do this. And then we define a resampling function, which just according to these state probabilities, will resample the historical observations and then combine them in new ways at the 21 trading day horizon. All right. So here you can see that we simulate 10,000 observation, 21 trading days ahead. This is what is done here, and you can go through the details of the code yourself to see if you can figure out how these computations have been made, compared to the theory, which is available in the portfolio construction risk management book or the time and state dependent resampling article. All right. So here, for this 1 month simulation, we just print the individual statistics just to assess if they are reasonable. So here you can see that the means are quite positive, and this is maybe due to this exponential decay that we introduce. So we use more of the recent history, we give it a higher weight, as many of you know, equity market performance in recent years has been quite good. But you see here that we still have some skewness, we still have some kurtosis, and if you look at these volatility numbers for the simulation and you compare them to the historical ones from the portfolio construction risk management book in chapter 2, then what you will see is that actually these volatilities have been estimated quite precisely compared to history, but the skewness and kurtosis and the drift is more favorable because we condition more on recent history compared to the full sample. All right. So then we proceed to this fictitious single stock P&L, and then you can imagine that we use these 10 broad equity indices as factors. So here we just generate some random factor loadings from minus 10% to plus 30%. So on average we allocate 10% to each of these factors. And of course, how we do this exactly, it's not so essential. It's just that we get some non-normal P&L based on this factor simulation. So just for you to understand these factor loadings more, we just illustrate for the first stock how the factor loadings are to each of the individual equity indices that we have simulated. So you can study this more yourself. You can even adjust it if you want. You can, if you have some real stocks, you can even use the simulation and estimate factor models for these stocks so that you can perform this simulation with real data. In this case, of course, we just we just work with the data that we are able to download and distribute with this Yahoo Finance. All right. So here we compute this stock return P&L by multiplying the factor simulations with these factor loadings. And here we just illustrate that the factor simulation, it has 10,000 scenarios for 10 factors, but for the stock simulation it has 10,000 scenarios for the 2,000 stocks. All right. So here we proceed to then perform the CVaR optimization using this simulations, and we use just long-only constraints and some entropy pooling posterior probability vectors. And you can read a lot more about entropy pooling in chapter 5 of the portfolio construction and risk management book. So first we initialize this CVaR optimization object with long-only constraints. That the exposure sum to 1, it's a default, so you don't have to specify it. And then we specify some return target. And here we just take the average of all these stocks and set it as the target for the portfolio that we want to minimize the CVaR for. So here you see that we run this efficient portfolio method from the CVaR optimization object, and you can see that we computed the CVaR efficient portfolio in 3.5 seconds in this case. So here in the next cell we just verify that all the constraints are satisfied and the return target is satisfied and all these things. So this tolerance is because whenever you do something numerical, even if you store some number in Python, there will be some numerical differences. So here we just validate that all the exposures sum to 1, that they are long only, and that this return target is satisfied for this portfolio. All right. So then we proceed to implement some entropy pooling views, and basically what we do here is just to say that the relative return of S&P 500 it increases by 10%. So it's like whichever stress test or view scenario you want to make here, you can adjust it. In our case, it's just to see how this CVaR optimization runs when we have a non-uniform scenario probabilities, and here you can see that it runs in 4.2 seconds. So it's a bit slower than the uniform, but it's still very, very reasonable given that we have such a large simulation. If you just use the usual linear programming CVaR optimization formulation, then what you will probably experience is that it's quite slow and then it's quite unstable. So I think many of these CVaR excuses, they come from that. And you can also look into some of the previous examples where we try to compare the fast implementation available in this open source package compared to just the usual linear programming implementation. And finally, if you want, you can also look into this CVaR optimization benchmarks repository, where you can see which kind of problems you can solve with CVaR optimization and how fast you can do it. All right. So finally, we just perform mean variance optimization. We initialize this mean variance class, and then it needs like a mean and a covariance matrix, and then again this long only constraints. We see how long it took. So in the prior case, you can see that it took 4.5 seconds, which is 1 second slower than for CVaR optimization in the prior case. In the posterior case, you can see that it took 4.6 seconds, which is also a bit slower than the posterior CVaR optimization. And this code has just been run on a normal laptop. So it's this computer that I'm recording from, so it's not like a big server or anything like this. This is the performance that you can get from CVaR optimization in high dimension on a normal server, not like massive cluster or anything like this. And then finally we verify for the variance optimized portfolios also that they satisfy all the constraints. All right. So if you ever hear people make the excuses that CVaR is unstable or not possible in high dimensions or something like that, you can share this example and say that it's not correct. It's definitely possible to do it, but it is of course much harder to implement these algorithms to run in a fast and stable way. So although this algorithm is faster than the normal linear programming formulation, then it's still not of production quality. So and this open source package does not give any guarantees that it will always run fast and it will always be stable. For that you need a subscription to the investment analysis module. All right, so this is the end of this video, and as always, if you want to maximize the performance that you get from this open source code, then you should give this repository a start.